Hello and welcome to today's lesson on applications of Taylor series. We're first going to look at the formula for a binomial series. Okay, so a binomial series is in the following form. So anytime you have 1 plus x to the k power, this is equal to 1 plus k times x. This will be over 1 factorial plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 over 3 factorial times x cubed, and so on and so forth. So let's take a look at the problem. We have a function. It's equal to 1 over 1 plus x squared. And we want to write this as a power series. Okay. So first of all, we want to write this in the form of a binomial series. We could say that we have 1 plus x raised to negative 2 power. Okay, so that basically tells me that k is equal to negative 2. So using that logic, we could go back into the formula for binomial series, and we could plug in everywhere there's a k, we can plug in negative 2. Okay, so we have 1 plus x to the negative 2. This will equal 1. And if we plug in negative 2 up here, that will give us negative 2 times x plus, if we plug in negative 2 here, that would give us negative 2 times negative 3 over 2 factorial x squared plus negative 2 times negative 3 times negative 4 over 3 factorial times x cubed. And this is going to go on and on and on. Okay, so we could simplify these. We'll have 1 minus 2x plus, now here we have negative times negative, that's positive 6 over 2 factorial, just 2 times 1, 6 over 2, which will be 3, so 3x squared. And then here we would have negative times negative times negative, that's a negative, so we'd have a minus. 3 factorial is 3 times 2, so that means we would cancel these two. We'll be left with the 4. X cubed. And if we see the pattern, we have 1 minus 2 plus 3 minus 4. It would continue like this, plus 5 x to the 4th, like that. So how can we express this in sigma notation? Well, sigma notation. Well, let's remember this first one. This is n equals 0. This is n equals 1. This is n equals 2. So on and so forth. N equals 3. So the x to the power, that's going to match the n. So I'll have n starting 0 to infinity. So I'll have x to the n. And then the number in front, notice that's always one more than the number of the n. So if n is 3, the number in front coefficient is 4. If n is 2, the number in front is 3. Okay, so that means in front of this will be n plus 1. And then notice the alternating signs. We have positive, negative, positive, negative, positive, like that. So that's going to be negative 1 to the n. Okay, so this would be the power series, and then you could double check. Let's see, negative 1 to the n. When we put a 0 in there, the 0 power is 1. When we put a 1 in there, that gives us a negative. So that gives us a negative 2, so that's good. Okay, so that means this would be the power series in sigma notation for the binomial 1 plus x to the negative 2. Okay, let's take a look at this next one. Express the integral of sine of x squared dx as a power series. So we already know what the sine of x is as a power series. Let's remind ourselves what that is. The sine of x would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and this kept going like this. Okay, so what we will do here is, because we have sine of x squared, everywhere we have an x, we're going to replace with x squared. Okay, so that gives us, in red, we have x squared minus x squared cubed to the third over 3 factorial plus x squared raised to the 5th over 5 factorial minus x squared raised to the 7th over 7 factorial, and this will continue like this. Okay, and just to simplify a little bit further, the power rule, we multiply the exponents, so this ends up giving us x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and that would be it. So this would be the power series for sine of x squared. Write a power series for arctan x and find the interval of convergence. Okay, so for arctan of x, let's remind ourselves what arctan of x was. So if we remember our integrals, Right, if we had the integral of dx over 1 plus x squared, this was equal to arctan of x plus c. Okay. So we're going to use this fact of the integral to help us out here. Okay. So namely the function we have within the integral, we have, if you want to think of it, we have like 1 over 1 plus x squared. Well, we're going to rewrite that slightly. The denominator we're going to rewrite as 1 minus negative x squared. So doesn't this remind us of something? Right? Isn't this kind of like how we would find the sum of a geometric series? Right? So our R basically, right? You want to think of it like it's geometric series. R is negative x squared. Okay. So if you want to take this a step further, we could then say that we could express this as the geometric series n equals 0 to infinity, where R is negative x squared, and we raise to the n power. Okay, so if we start plugging in our n equals 0 and n equals 1 to get the terms of this power series, we would end up with 1 when n is 0. When n is 1, we would have minus x squared. When n is 2, we would have negative x squared times negative x squared would be positive x to the 4th. When n is 3, we'd have negative x to the 6th. So on and so forth. Okay, so since we know that the arctan of x is equal to the integral of dx over 1 plus x squared, so we could say that this will be equal to the integral of our power series we have up here, 1 minus x squared plus x to the 4th minus x to the 6th Okay, and we could integrate this piece by piece. So we would have x minus, I just integrate term by term. Integral of 1 is x, integral of x squared would be x to the 3rd over 3, integral x to the 4th, x to the 5 over 5, minus x to the 7 over 7. When we integrate, we're going to have to, don't forget about the constant, plus c, and we get the rest of the terms as well. Okay, now the c we don't have to worry about, because think about it this way: if we have arctan of 0, it equals 0, so therefore it forces c to be 0. So we have arctan of x equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 dot dot dot. Okay. As for interval of convergence, so we know that the series converges. So if we have x squared it'll converge for x squared is less than 1. So the x squared and the absolute value redundant. So for example, we could just say this is absolute value of x is less than 1, which tells us that x would have to be less than 1 and greater than negative 1. And we can always show that the series converges for x when it's 1 and negative 1. So the interval of convergence would be negative 1 to 1. And that would be it. Evaluating indeterminate forms. So we could use Taylor series to evaluate some forms that are indeterminate. So one of the ways we could solve a problem like this, we have the limit as x approaches 1 of ln x over x minus 1. We can try to represent ln x, natural log of x, as a Taylor series. Okay, in fact we could do a Taylor series of ln x centered at x equals 1. Right, so we could do Taylor series and the whole reasoning behind that is because when we were centered at x equals 1, all the polynomial terms will have x minus 1 as a part of it. And we see the denominator here is x minus 1. So that works out nicely. Okay, so I'll leave that as an exercise for you guys. So if it's ln x centered at x equals 1, all the terms of the Taylor series will give us x minus 1 minus 1/2 x minus 1 squared, and this will continue like this. Okay, so what we could do now is if we take the limit as x approaches 1, we're going to replace ln x with the Taylor series. So x minus 1 minus 1/2 x minus 1 squared. And this is all divided by x minus 1. So take each term piece by piece and divide it by x minus 1. So we have x minus 1 divided by x minus 1, which will be 1 minus, and then divide out x minus 1 squared with x minus 1, so we have 1/2 of x minus 1 plus and if we apply the limit as x approaches 1, well, this one stays, but then if we plug 1 in here, this one goes to 0, and then any of the other ones, when we plug 1 in, will go to 0. So the only thing left is the 1, so the limit here would be 1. Okay. Let's find the first 3 non-zero terms of the Maclaurin series for tangent of x. So we could use our knowledge of tangent of x so we know that tangent of x is equal to sine of x over cosine of x. And we know what the Taylor series are for both sine x and cosine x. So for sine x we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, so on and so forth. For cosine we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and this will continue like this. So we could actually do a long division between the Taylor series for sine x and cosine x, and we could come up with the first 3 non-zero terms for tan x this way. Okay, so I'm going to divide the sine x polynomial by the cosine x polynomial. Okay, so I have x minus, now the coefficient here for the x cubed would be 1 over 6, right? And then we have plus 5 factorial, so 1 over 120 x to the 5th and then we have the minus. In fact, these should be minuses because they alternate. And then we're going to divide by 1 minus 1/2 x squared plus 4 factorial will be 24, so 1 over 24 x to the 4th. Okay, so alright, so we have x divided by 1, so we're going to take the leading terms. X divided by 1 will be x, so we have x, so x times everything here would give us x minus 1/2 x cubed plus 1 over 24 x to the 5th minus subtract. Okay, so the x's would cancel. I have negative 1/6 x cubed minus negative 1/2 x cubed. That would give us 1/3 x cubed. And then 1/20th minus 1/24th, that would give us a minus 1/30th x to the 5th. Okay, so next I need to get rid of the 1/3 x cubed. Okay, so that means I have to multiply 1 times 1/3 x cubed. So plus 1/3 x cubed. 1/3 x cubed times 1 is 1/3 x cubed. 1/3 x cubed times negative 1/2 x squared. That would be negative 1/6 x to the 5th. And then so on and so forth. I only need the first 3 terms, so that's why I'm not going to go further and multiply with the 1/24 x to the 4th. Okay, so I subtract here. So I have my 1/3 x cubes are gone. I subtract my negative 1/30th minus my negative 1/6th. That gives me 2/15 x to the 5th. And then to cancel the 2/15 x to the 5th, I would have plus 2/15 x to the 5th. Okay, so those would be the first 3 terms of my Maclaurin series for tangent. Okay. Okay, let's take a look at this next problem. It says to evaluate the limit as x approaches 0 of sine x minus tangent of x over x cubed. Okay, so we know what sine x is. Right? Sine x is x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. We just did tan x up to 3 terms. So tan x was x plus 1/3 x cubed. I could say is x cubed over 3 plus 2/15 x to the 5th. Okay, so we could subtract these term by term. Okay, we could subtract these term by term. So sine x minus tangent x. So if we subtract these term by term, we have x minus x 0. We have negative x cubed over 3 factorial minus x cubed over 3. So that would give us negative x cubed over 2. And then we have x to the 5th over 5 factorial minus 2/15 x to the 5th. That would give us minus x to the 5th over 8. And this would continue like this. So what we could do to help us out a little bit, we could factor out an x cubed. If we factor out an x cubed, then we have negative 1/2 minus x squared over 8 minus like that. And keep in mind the original problem, we had the x cubed on the bottom. So we're going to divide this by x cubed. So limit as x approaches 0. Okay, so that means when these divide, these two x cubes are gone. So we have limit as x approaches 0 of -1/2 minus x squared over 8 minus ... and x approaches 0, so as this becomes 0, this is gone, right? And then all the rest will be gone. So all we'll be left with is -1/2. Okay. Let's take a look at this next one. Limit as x approaches 0 of 1 over sine x minus 1 over x. So we could rewrite this if we multiply, we get the common denominator. So that means I would multiply this by x over x, and then this one I would multiply by sine x over sine x. So I have x minus sine x over x times sine x. Okay, so if I have this, then I can take for the top, and using the Taylor series for sine x, I could say this is x minus, and then in parentheses, my Taylor series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... For the bottom, I would have x times my Taylor series for sine, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus so on and so forth. So if I distribute the minus into the top, I have my x minus x, that goes away. And if I distribute the minus throughout the rest of these, I have x cubed over 3 factorial minus x to the 5th over 5 factorial plus, like that, over, and if I distribute the x to the bottom, I would have x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus so on and so forth. So the next part I could do is I could factor out an x cubed from the top, and I could factor out an x squared on the bottom. Okay, so look at what happens when I do that. So if I factor out an x cubed, I have 1 over 3 factorial minus x squared over 5 factorial plus over x squared, that would be 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial Okay, so then what I could do is simplifying the x cubed and the x squared. I'm just left with an x x times 1 over 3 factorial minus x squared over 5 factorial over 1 minus x squared over 3 factorial plus, I'm going to keep this the same now, like that. So if I apply the limit here, as x approaches 0, what's going to happen? Well, I'll have 0 from the x times, and over here this will be about the same, right? We have x squared over x squared, it's a negative over negative. Okay, so that means this will end up becoming 0. Okay, and that's about it. We close it up with just a table with some frequently used Taylor series. Okay, you guys could pause and just look at these again. These are some of the common ones we talked about, okay, over the past couple sections. And if you guys have any questions, just email me or bring it up during the lesson. Okay, have a good day, have a good night. We'll see you guys soon. Bye-bye.